Alright, let's try this one. So the question would be, figure out for which x's the series converges. And to do that, we have a bunch of tools at our disposal. For a couple of weeks we've already been spending all our energy trying to figure out different tests that help us answer precisely that question. On this one I think the root test will do. Let's try it. So you take the nth root. The nth root test says we got to look at the nth root of the absolute value of a n's. Right, so this would be something like this: x minus 3, the absolute value, over 2 to the n, and then we got to do the nth root. That becomes absolute value of x minus 3 all over 2. That's what you get, and then you take the limit as n goes towards infinity, but there's no sense in taking the limit here because there is no n. So the limit as n goes towards infinity is equal to itself, x minus 3 over 2. And so we got ourselves our limit. Now the ratio test says that whenever this happens, then our original series, x minus 3 over 2 to the n raised to the n, behaves, as far as convergence and divergence goes, behaves like x minus 3 over 2 to the n. Right? So this is a geometric series. Well, that's kind of silly. You could have just looked at it and done that. But okay. This tells us it behaves like that, and then that we can conclude then that will converge if x minus 3 over 2 is less than 1. Well, then we have convergence. If x minus 3 over 2 is less than 1, we have convergence. So this means that we have convergence if x minus 3 over 2 is stuck between 1 and negative 1, which would mean that we have convergence if x minus 3 it's stuck between 2 and negative 2, which means that we have convergence if we add 3 to everything. That would give us 5 here, x here, add 3 to that, that would give us 1 here. That means we have convergence if x is stuck between 1 and 5. Of course we have divergence outside, and at the endpoints the test is inconclusive. And so you want to check, here's what we know so far. It converges for the ratio between 1 and 5. We have convergence here, we have divergence here, we have divergence here, and we don't know about those endpoints right there. So we check each of them separately. So we check, for example, x equals 1. Check it into the original series there. That will give you negative 2 to the n over n. That will give you summation of negative 1 to the n. That doesn't converge, that diverges. Then we check the other endpoint, which would be 5. X equals 5. At 5 it'll give you summation of 1 to the n, which will not converge. So the endpoints should not be included, meaning that our interval of convergence is from 1 to 5. Also, sometimes you should know, some books talk about the radius of convergence. It's kind of a deeper idea, maybe beyond the scope of this class, but maybe I could say a couple words about that now. So if I go from negative 1 to 5, there's some midpoint here. Sorry, from positive, that's positive 1 to 5. There's some midpoint here, maybe the midpoint is 3. And if you were to look at the complex plane, there are numbers not just on the number line, but above and below. And you could create a circle where for every one of these points, no matter what it is, even if it's complex, I mean, for example, 4 plus I, that's in the circle, the series will still converge if x is complex number, non-real, so long as it's in this circle. And so often, instead of saying the interval of convergence, which would just reduce you to the real number line, that's the interval of convergence, people talk about the radius of convergence, which is a more generalized concept, a more powerful concept actually. So you might hear that thrown around sometimes here and there. Thought you should know. Anyways, come back, we'll do more examples. We'll see you guys.